Welcome to Developmental Biology. Today we are exploring a profoundly important topic, teratogenic agents and effects. We will learn exactly how external environmental factors can disrupt the delicate, complex process of embryonic development. More importantly, we will discover how scientists mathematically predict these impacts to establish safety guidelines and protect human life. Let us dive in. To begin, imagine you are building a magnificent, complex house from a set of delicate blueprints. If a storm hits or toxic materials are delivered right when the foundation is being poured, the entire structure is permanently compromised. However, if that same storm hits after the house is fully built, it might only break a window, which is easily fixed. In human development, the baby growing inside the womb is exactly like that house under construction. The storms or toxic materials represent harmful substances from the outside world. Understanding these intruders is like learning how to protect the construction site. Now that we have our analogy, let us formally define what these intruders are. In developmental biology, a teratogen is any environmental agent that causes a structural abnormality or birth defect in a developing embryo or fetus. The word itself has fascinating origins. It comes from the Greek root terato, which translates to monster or marvel, and genesis, meaning creation. It is crucial to understand that these are not genetic mutations inherited from parents. Instead, teratogenic effects are strictly caused by external factors, like chemicals, viruses, or radiation, interfering with normal developmental pathways, such as cell division and tissue differentiation. Understanding these external factors is not just academic, it is a matter of life and death. Without this knowledge, we would not know which medications are safe for pregnant women. A tragic real-world example occurred in the 1950s and 60s with a drug called thalidomide. It was widely prescribed for morning sickness, but it resulted in thousands of babies being born with severe limb deformities. Today, the lessons learned from this tragedy are used to strictly regulate pharmaceuticals, create guidelines for alcohol and tobacco, and protect pregnant workers from harmful industrial chemicals. Having seen the devastating real-world impact, we must ask, how do scientists predict and prevent this harm? They use mathematical models. One of the most fundamental concepts in toxicology and teratology is the threshold dose-response model. This model assumes that an embryo can safely tolerate a very small amount of a substance without any harm whatsoever. The embryo has natural defenses. But once the exposure crosses a specific limit or threshold, the damage begins to scale up rapidly. We can represent the magnitude of this teratogenic effect mathematically using a linear threshold equation. This brings us to the mathematical heart of our topic. The formula is E equals K times the quantity D minus D sub TH. Conceptually, this tells us that the severity of a birth defect is directly proportional to how much the actual dose exceeds the safe limit. Let us break down the symbols. E represents the magnitude or severity of the teratogenic effect. The variable K is the teratogenic potency constant, telling us how aggressive the agent is. D is the actual dose the embryo is exposed to. Finally, D sub TH is the threshold dose, the maximum safe amount. If D increases beyond this threshold, the severity E increases linearly. Now that we have our formula, let us see this with a concrete example. Imagine a researcher studying a chemical solvent. We are given a safe threshold dose of 15 milligrams per liter and a potency constant of 2.5. The embryo is accidentally exposed to an actual dose of 35 milligrams per liter. We need to find the magnitude of the effect. We start by substituting our values into the threshold equation. We subtract the safe threshold of 15 from the actual dose of 35, which gives us an effective toxic dose of 20. Finally, we multiply this excess dose by the potency constant of 2.5. This gives us a final severity score of 50, meaning significant structural damage will occur. So we have successfully calculated the effect of a single chemical. This leads us to an important practical application, comparing different drugs to see which is safer. In the real world, pharmacologists often have to choose between medications. We will look at drug A, which has a low threshold but high potency, and drug B, which has a high threshold but low potency. By calculating the teratogenic effect for both drugs at the exact same exposure level, we can objectively determine which medication poses a greater threat to the developing fetus. Let us perform this comparative analysis now. Let us begin our comparison by calculating the damage caused by drug A. We are given that the fetus is exposed to a total dose of 50 milligrams. For drug A, the safe threshold is very low, just 10 milligrams, and its potency constant is quite high at 4.0. We substitute these specific constants into our equation. Subtracting the threshold of 10 from the dose of 50 leaves a massive effective toxic dose of 40 milligrams. We then multiply this large toxic dose by the high potency constant of 4.0. This results in a severe teratogenic effect magnitude of 160 units. Now we shift our focus to drug B to see how it compares at that exact same 50 milligram dose. Drug B has a much higher safe threshold of 40 milligrams and a lower potency constant of 1.5. We substitute these new values into our formula. Subtracting the threshold of 40 from the dose of 50 leaves an effective toxic dose of only 10 milligrams. Because the threshold is so high, most of the drug is processed safely. Multiplying this small toxic dose by the lower potency of 1.5 gives us a final effect magnitude of just 15. Physically, this demonstrates that drug A is vastly more dangerous, proving that a drug's danger depends heavily on its specific threshold and potency. To visually reinforce what we just calculated, let us look at the threshold dose-response graph. On the horizontal axis, we have the dose of the teratogen in milligrams. On the vertical axis, we have the magnitude of the teratogenic effect. Notice the flat horizontal line starting from 0? This is the safe zone, where the embryo experiences no developmental defects because the dose is below the threshold. The critical point is where the arrow points to the threshold dose. Once the exposure crosses this exact point, the graph slopes upward into the toxic zone. The steepness of this line represents the potency constant. This visual perfectly captures why keeping exposures below the threshold is absolutely critical for safe embryonic development. We have covered a lot of ground today, so let us summarize the most important ideas. First, teratogenic agents are external environmental factors, like chemicals or radiation, that disrupt embryonic development and cause birth defects. Second, the danger of these agents is not just about the total dose. It depends heavily on the specific potency and whether the exposure exceeds the embryo's safe threshold limit. Finally, by using mathematical models like the threshold dose-response equation, scientists can predict potential harm and establish life-saving safety guidelines. You now have a solid understanding of how teratogens work and how we quantify their effects.